Hello, everybody. This is Dr. Weber, and this is your mini lecture about current. And this image here is a bunch of different resistors. If we remember from lab, our resistors have color codes, color bands on the side that tell us what the amount of resistance is for each particular resistor. So the electric current, which we have also seen in lab already, is the rate at which charge flows. And here's the equation for current, one equation for current. Current is defined as the capital letter I, and that equals to the amount of charge that can flow through a cross-sectional area per unit time. So here we have charge flowing through a cross-sectional area. And the units of charge are not charge, sorry, the units of current are units of amperes. 1 ampere is equal to 1 coulomb per second. If you watch the crash course video about current, you will know a few of these things that I'm already talking about here. But we choose a particular direction for what we call the conventional current. And this current, this flow of charge, flows from high voltage to low voltage. And I forgot to mention to you, behind me, I have some current flowing. This is water flowing over the edge of one part of the Niagara Falls. And just like how water has current, we can think about electric current as being a flow of charge. And just like how the water flows from regions of high gravitational potential energy to regions of low gravitational potential energy, our current flows from high voltage to regions of low voltage. Okay, and our current flows from the positive end of our battery, or the positive terminal of our battery, to the negative terminal of the battery. And so here is a schematic of how we might have a circuit diagram. And we've got our battery here. We've got the positive terminal represented by the longer line here, our negative terminal represented by the shorter line here. Our current is flowing from this positive terminal around our circuit to the negative terminal. This symbol represents a resistor, which we will talk about later, and this current in this particular diagram is flowing clockwise, the direction of a clock. Now, up here is the same idea. Down here was the schematic. Up here we have the actual thing in real life. We've got, let's say, a car battery. We've got current moving through the wires to light up a headlight, and then that current flows to the negative end of the terminal. Now, this flow of current is opposite the direction that negative charges move. So really, when we're talking about current, we're talking about the flow, or the direction in which positive charges would flow within our circuit. Now, the flow of positive charges in one direction is equivalent to the flow of negative charges in the opposite direction. So why do we choose the particular direction that we do for current when it's really the electrons that are the charge carriers? Well, we can thank Benjamin Franklin for that. And if you watch the crash course video about current, you will learn more about Benjamin Franklin and why we choose current in the direction that we choose it. Electric signals travel at speeds on the order of 10 to the 8 meters per second. So this is a significant fraction, pretty close to the speed of light. Remember that the speed of light is 3 times 10 to the 8 meters per second. So how fast do the particles move inside our wires? Our particles, our electrons that are, or our charges that are moving inside our wires. The actual, what we call the drift velocity of the electrons, is only about 10 to the minus 4 meters per second. So that seems pretty small, right? Our charge carriers take something like a random walk inside the wire, the conductor, but with some particular direction in mind. And so our electron here, our charge carrier, is bouncing around inside the conducting wire here. the sharp changes in its direction here are due to collisions with other atoms inside the conductor. So even though it takes something a little bit like a random walk, in general, the net motion of these electrons is going to be in one particular direction. And we note that the net motion of our electrons here is opposite the direction of the electric field inside the conductor and opposite the direction of this current too. Now, our current depends on the average speed of charge carriers, the number of these charge carriers per unit volume, and the size of the charge carried by each of our charge carriers. So here we have an equation that shows the amount of like the rate of change of charge, and that is equal to this whole quantity here, which represents the number of mobile charge carriers per unit volume. That means the number of charge carriers per unit volume that are free to move around, free electrons essentially. And that number is equal to the number of our electrons times some volume. So we've got our area here, cross-sectional area of our wire, times delta x, some distance x, okay? So our cross-sectional area times some length, so we're essentially sweeping out a volume of a cylinder here, and then we multiply that by q. Our distance, or our change in distance, is equal to some velocity times time. And so we can replace our delta x here with a drift speed or drift velocity times time, since x is equal to v times t. So here we replace delta x with v, drift speed times time, right in here, and then we can get a new equation here. And so q is equal to n. This is our number of charge carriers times cross-sectional area times drift speed times time times the charge of our charge carriers. Now, we can rearrange this, and we remember that current is equal to the change in the amount of charge per unit area over time. And so we can solve this equation here. If we say that I is equal to delta Q over delta T, then I has to equal our number of carriers times charge times the drift speed times our cross-sectional area A. Okay, and we're going to use this equation in order to solve a problem that I will work through next.
We're going to calculate the drift velocity of electrons inside a copper wire. So here we have a copper wire that has a cross-sectional area of 3 times 10 to the minus 6 meters squared, and it carries a current of 10 amperes. The density of copper is 8.92 grams per cubic centimeter, and the atomic mass of copper is 63.5. With that information, and assuming that each copper atom contributes 1 free electron to the metal, those free electrons are what's going to move inside the wire as our charge carrier to create the current, we're going to find the drift speed of the electrons in this wire. So our conventional current, we're going to say, is running in this direction, which is also the direction of the electric field. We know that our electron, the charge carrier for electricity, is going to travel in the opposite direction of the conventional current. So its drift velocity is going to be opposite the direction of the conventional current. And our little electron here makes sort of a random walk on its way through the wire here. But eventually, and on average, it has some speed that takes it opposite the direction of the conventional current. So we want to find, we're going to find the drift speed. To start this problem, we've got A, and we need to find this drift speed, VD equals question mark. I'm going to start by writing down this definition for current. Current is equal to N which is our number of charge carriers per unit volume, times the charge on each of those charge carriers, times our drift speed, times the cross-sectional area of our wire. Now, we want to solve for the drift speed, so I'm going to rearrange this. Basically, I have to divide this side by NQA. Well, divide both sides by NQA. So the drift speed will be I divided by NQA. Okay, well, we know the current was 10 amperes. We know the cross-sectional area. We know the charge on an electron. But what is our number of charge carriers per unit volume? In order to get this, we are going to have to think a little bit more creatively. We want to find our number of charge carriers per unit of volume, per unit, I'll say per unit V. Okay, that's going to equal our number of electrons per mole of the copper divided by the volume per mole of our copper. So how many electrons are there per mole? Avogadro's number of electrons. This is going to be 6.02 times 10 to the 23 electrons per mole. And then we're going to divide it by the volume per mole of copper. Now, how do we find this volume per mole? Well, that volume per mole is going to be your mass per mole divided by the density. So volume is your mass over density. This is going to be our mass per mole divided by the density of copper. We know that copper has an atomic mass of 63.5 atomic mass units. And that's something you can look up off of a periodic table. So this means that copper, if copper has an atomic mass of 63.5, that means that 1 mole of copper is 63.5 grams of mass. Okay, so the mass per mole is 63.5 grams. And then we're going to divide it by the density of our copper, which was 8.92 grams per cubic centimeter. Okay, so our grams cancel here and here. And so this tells us that our volume per mole is 7.12 cubic centimeters. All right, but you know, we are working over here on this in this problem. Our cross-sectional areas in units of meters squared. We're going to eventually find our drift speed in units of meters per second. So we want to convert this volume in centimeters cubed into meters cubed. So how do we do that? Well, you think about a box that has length, width, and height of 1 meter. 1 meter is 100 centimeters. So if you have a cube, the volume of the cube is the length times width times height. So we could have 1 meter times 1 meter times 1 meter gives us the volume of that cube. Or 100 centimeters times 100 centimeters times 100 centimeters gives us the volume of 1 meter cubed. So in 1 meter cubed, there's 100 centimeters times 100 centimeters times 100 centimeters, or 100 centimeters cubed. Okay? So our cubed centimeters cancel here. You take 7.12 divided by 100 cubed, and that gives us a volume per mole of this copper of 7.12 times 10 to the minus 6 meters cubed. Okay, that's what I'm going to put in here for my volume per mole, so we can find the number of charge carriers per unit volume. So this is 7.12 times 10 to the minus 6 meters cubed. So this tells us that we're going to have 8.46 times 10 to the 28 electrons per meter cubed. That is our number of charge carriers per unit volume that we need to put right here into our equation for drift speed. Okay, so in order to get this number of charge carriers per unit volume, we had to know something about the density of the wire. It was made up of copper, and we also had to know something about the atomic mass of copper in order to do that. So this is going to equal now, we've got our current is 10 amperes, and we divide that by our number of charge carriers per unit volume. So we've got 8.46 times 10 to the 28 electrons per meter cubed. Okay, we multiply that by the charge on each of our charge carriers. We've got electrons, and so that's, well, we're just going to take the absolute value of that unit of charge. So that's going to be 1.6 times 10 to the minus 19 coulomb. And then we're going to also multiply that by the cross-sectional area. So that's 3 times 10 to the minus 6 meters squared. Okay? Absolute value, because we're just thinking about the magnitude of this drift velocity, so the drift speed. So we can take the magnitude of this charge here. Then we get that our answer is 2.4 times 10 to the minus 4 meters per second. That is our drift speed of the electrons inside this copper wire. Let's put this drift speed in context. We are going to now use the ideal gas model to compare this pretty small, you might think, drift speed with the random RMS, root mean squared, speed an electron would have at 20 degrees Celsius. So we're going to find the RMS speed of a cloud of electrons at 20 degrees Celsius. This is from last semester when we were talking about thermodynamics. The RMS speed of a gas is sort of the average speed of our particles inside a gas. Now, to find this, we'd have to look back at our equation sheet from last semester. The RMS speed of a gas is equal to, of an ideal gas, the square root of 3 times the Boltzmann constant times the temperature in degree Kelvin, or sorry, just in Kelvin, and we divide it by the mass of our molecules in the gas. In this case, they would be electrons. So this is going to be 3 times, well, our Boltzmann constant was 1.38 times 10 to the minus 23 joules per Kelvin. And we want this temperature in units of Kelvin. To take 20 degrees Celsius to Kelvin, we have to take 20 degrees, or 20, and add it to 273. And that will get us from 20 degrees Celsius to that temperature in Kelvin. And we divide it by the mass of our electron, which is 9.11 times 10 to the minus 31 kilograms. We take the square root of that, and that gives us an RMS speed of a cloud of electrons of 1.15 times 10 to the 5 meters per second. Now let's compare our RMS speed, let's do that here, that RMS speed to the drift speed of our electrons inside the wire here. So if we do that, we've got 1.15 times 10 to the 5 meters per second. We divide that by, here, our 2.46 times 10 to the minus 4 meters per second. So we find that our RMS speed of the electrons in the gas is 4.68 times 10 to the 8 times greater than the drift speed of an electron in a wire. The drift speed of our electrons inside this wire is only about 1/billionth of their random thermal speed. Okay, so that number seems super small, but then you're going to ask yourself, okay, so if the drift speed of the electrons is so small, Why is it that an electric signal seems to move so fast when you flip the light switch? Well, you can think about our analogy of current as like a flow of water through a pipe. So if the pipe is already filled with water and we force a little drop of water into one end, a little drop must be pushed out of the other end, assuming that our water was incompressible. In a conductor, this electric field that's driving the travel of free electrons, that electric field is traveling at the speed of light. So when you flip on a switch, the message for our electrons to start moving reaches them at a speed of about 10 to the 8 meters per second. Not quite, but pretty close to the speed of light. So this signal to tell the electrons to move whenever you flip the switch, that signal travels at pretty close to the speed of light. But those little electrons themselves only drift with their random walk through the wire at the speed of about 2.4 times 10 to the minus 4 meters per second, at least in this problem for our copper wire.